Welcome to Mrs. Arel's classroom. In this video, we will continue to practice Introductory Physics MCAS open response release questions for heat transfer. Before you get started, get ready with some stuff like paper, pencil, calculator, formula sheet. Do each problem on your own first, and then review your solution based on the video discussion. Correct your solution as well. Number 23, release 2017. Pause and try on your own first. Read through all the questions, underline keywords, and sketch any useful pictures. A sample of ice is heated in a closed container. The sample melts and then evaporates. So I've drawn a picture here where I have the closed container. Here's the sample of ice, and the container is being heated. The ice melts and then evaporates. The container is then placed outside on a very cold day. The sample condenses and then freezes. So here we have the same container in experiment 2. Now there's water vapor. That water vapor condenses and then freezes back into ice. So heat is leaving the system to the colder air outside. The average molecular kinetic energy of the sample is measured during these changes. Identify the tool used to measure the average molecular kinetic energy. During which two phase changes does the sample absorb energy? Describe the direction of heat flow between the sample and the air in the container as the sample condenses. Does the sample ever release thermal energy without changing temperature? Explain. To identify the tool to measure the average molecular kinetic energy, which is also known as temperature. So the average molecular kinetic energy is temperature, and a thermometer is used to measure the temperature. The bolded words are the ones that are used in the question that I repeat in the answer to focus my answer better. During which two phase changes does the sample absorb energy? So if I look at my previous sketches, I can see that the sample is absorbing energy, in this case in experiment 1. The sample absorbs energy during experiment 1 where the ice is melting, so it's going ice to liquid, solid to liquid, and then evaporating to water vapor, liquid to gas. So you need energy to melt and then evaporate. Thermal energy is absorbed in these cases because liquid has more thermal energy than the solid, and a gas has more thermal energy than a liquid. Describe the direction of heat flow between the sample and the air in the container as the sample condenses. As the sample condenses into a liquid, which is our experiment 2, heat flows from the sample to the air in the container. Also, the container is conductive, so the heat flows outside as well, but the question is asking us just about the air inside the container. Does the sample ever release thermal energy without changing temperature? Anytime you have a phase change of a substance, the temperature does not change. So, water vapor releases thermal energy while condensing into a liquid. And then the liquid releases thermal energy while freezing to ice. So that gives us the answer. Now explain. Thermal energy is released in these cases because ice has less thermal energy than a liquid, and a liquid has less thermal energy than a solid. Number 45, release 2012. Pause and try on your own first. Read through all of the questions, underline keywords, and interpret any diagrams given. A can of juice at 20 degrees Celsius is completely submerged in a closed, insulated container filled with water at 4 degrees Celsius, as shown in the diagram. So I can see the diagram. Here's my 20 degrees Celsius can of juice, and it's warmer than the 4 degrees Celsius water. And it's completely submerged, which means it's under. The container is surrounding all of that, and it says it's insulated, which means very little to none heat transfers outside of the container or into the container. Describe what happens to the temperature of the can of juice and the temperature of the water in the container within the first few minutes after the can is submerged. Explain. So first few minutes is considered a fairly short period of time. Now we need to think about what happens in that short period of time. After 4 hours, will the can and the water have the same temperature or different temperatures? Explain. Estimate the numerical values of the final temperatures of the can of juice and the water after 4 hours. Explain your answer. So let's describe what happens to the temperature of the can of juice and the temperature of the water within first few minutes. Within the first few minutes after the can is submerged, which is a fairly short time, the temperature of the can of juice decreases and the temperature of the water increases. The can of juice and the water start at different temperatures, which causes heat transfer from the hotter can of juice to the colder water. Heat is always transferred from hot to cold. After 4 hours, will the can and the water have the same temperature or different temperatures? Explain. After 4 hours, a longish time, the can and the water will have nearly the same temperature. Given a long enough time, temperatures tend to come to the same point. As the heat transfers from the hotter to the colder substance, while their temperatures are different, heat transfer stops when the can of juice and the water reach the same temperature, which is also called thermal equilibrium. Estimate the numerical values of the final temperatures of the can of juice and the water after 4 hours. An estimate is not an exact calculation. You make an educated guess and you justify it. We need to think about the equation for heat transferred, heat absorbed, or heat released, which is mass times specific heat times the change in temperature. So the same amount of heat is transferred to the water as is lost by the can. Juice is almost like water, and juice has nearly the same specific heat. So what does that mean? It means that the Q, this equation, for the amount of heat gained by the water from the can is the same Q as the heat lost by the can. So these values are the same in both cases, for the water and the can of juice. Now for the water, the mass is bigger, so it's going to have to go through a smaller temperature change to come out with the same energy that it gains or absorbs. And the can of juice, being with a small mass, is going to have to go through a much bigger temperature change to make up for that small mass. Because on this side we're multiplying all these things together and we have to come out with the same amount of energy, gained or lost. So the difference in mass makes the difference in how many degrees something gains or loses in temperature. After 4 hours, the final temperature of the can and the water will be about 6 degrees Celsius, closer to the initial water temperature than the can temperature. Because there is more water than juice, the water temperature will increase only a little and the can temperature will decrease a lot. So more mass means less temperature increase for the same energy, and less mass means more temperature change. Number 44, release 2013. Pause and try on your own first. Let's read through all of the questions, underline keywords, and sketch any useful pictures. A student heats to a 200-gram sample of water from 20 degrees Celsius to 80 degrees Celsius. The specific heat of water is 4.18 joules per gram per degree Celsius. Specific heat, just looking at its units, is the amount of joules or energy needed to increase the temperature of 1 gram of something by 1 degree Celsius. So water needs about 4 joules to increase its temperature by 1 degree Celsius for 1 gram of water. Different substances have different specific heats, and specific heat is unique to substances, so it can be used to identify substances. Calculate the thermal energy absorbed by the water. The student is going to boil the water, We're going to describe what happens to the temperature of the water as it boils and explain. The student repeats the experiment, this time placing a small block of iron into another 200-gram sample of water. So he places a block of iron into the same mass of water as it was in experiment 1. This is 200, this is 200. The specific heat of iron is about a half a joule, or about 0.45 joules per gram per degree Celsius. Both the iron and the water are initially at 20 degrees Celsius and are heated to 80. So what we see there is that the temperature change here is the same in experiment 2 as it was in experiment 1. So delta T is the same. Compare the amount of thermal energy absorbed by the water in this experiment with your calculation in part A. How much energy does the water absorb? And then describe how repeating the second experiment with a block made of a material with a greater specific heat will affect the amount of time it takes to heat the block. We have a third experiment where you have the same amount of water, but now you put a material in there that has a greater specific heat, which means there's more joules needed of energy to raise 1 gram of it by 1 degree Celsius. So we're going to compare that experiment to the second one and how that will affect the time of heating the blocks. For the first case, we're going to have to do a calculation. So labeling all the given variables, we have mass is 200 grams. The starting or initial temperature, Ti, is 20 degrees Celsius. The final is 80 degrees Celsius. And specific heat, which is labeled by the variable C, is 4.18 joules per gram per degree Celsius. We need to find heat, or thermal energy, which is Q. On the formula sheet, the equation that relates these variables is Q equals mc delta T. The description of the variables say that C is a specific heat and delta T is changing the temperature. Changing the temperature means subtracting final temperature minus initial temperature, and that's the symbol delta, which tells you to subtract. If we plug in the values, 200 for mass, 4.18 for specific heat, and final minus initial temperatures, we get that the heat absorbed by the water is about 50,000 joules, or 50,160 joules. So the temperature of the water increases 60 degrees Celsius, and this is the amount of heat that's absorbed by the water. Heat has the same units as energy. In this case, it's joules. The student then boils the water. Describe what happens to the temperature of the water as it boils. Explain. So boiling is a phase change. As the student boils the water changes phase from a liquid to a gas. During the phase change, the temperature of the water stays the same. The student repeats the experiment and does the second one with the iron in the water, but it's asking us to compare the amount of thermal energy absorbed by the water only in this experiment with what we got in part A. So if we look at how much energy got absorbed by the water and what it depends on, we see that the amount of thermal energy depends on mass, specific heat, and change in temperature. The amount of thermal energy absorbed by the water during the second experiment is going to be the same as calculated in part A. That's the answer. Now let's explain that answer. Water absorbs the same amount of heat, Q, in both cases because Q depends on the water mass, its change in temperature, and its specific heat, which are all the same in both experiments. Obviously, more energy is going to be absorbed in total by the system because there's also an iron block being heated, but they're not asking about that. They're just asking about the water heat absorbed. Describe how repeating the second experiment will change the time it takes for the sample to heat. So we have this block now in experiment 3 that has a higher specific heat. If the student repeats experiment 2 with a block that has a greater specific heat, it will take more time to heat the new block to the same temperature. Specific heat is how many joules are needed to raise 1 gram of something by 1 degree Celsius. The substance with the greater specific heat needs more energy to increase its temperature by the same amount, so it also was going to need more time. The key concepts in this video are that heat transfers from hot to cold, hotter to colder substance. When the temperature changes during heat transfer, and we're not talking about phase change, the molecules of the colder substance will gain kinetic energy and start to move faster, and the molecules in the hotter substance will lose kinetic energy and slow down. And kinetic energy is, when you average it out for all the molecules or atoms in a substance, is the same as temperature. During phase change, here the temperature doesn't change. In this case, substances will release energy when changing from gas to liquid, which is condensation, and from liquid to solid, which is freezing. Substances absorb energy when going from solid to liquid, melting, or from liquid to gas, evaporating. The heat transfer equation is on the formula sheet, and it's Q equals mc delta T. The variables are also described on the formula sheet. Remember that C, the specific heat, is unique to different substances. So the amount of energy it takes to heat something by 1 degree Celsius for 1 gram is different for different materials.